All right. So good day, class. I hope you're getting through with the lesson quite smoothly. And if ever you have questions, feel free to ask me directly via the Google chat and or send me an email via the provided email that I gave in and uploaded in your Canvas sign. Okay. Um, I understand a pre-recorded and uploaded several lessons about force system resultants, specifically about part two. And for the last part of the force system resultants, we're going to be going over the concept of simplifying forces and couple systems. Okay. All right. So those are not icebergs, but they just represent a particular system, whether that be a beam, whether that be a 2D or 3D problems, basically. The concept behind simplification of forces and couple moments is as it is. We simplify multiple force vectors and or multiple moment vectors, and then we sum them up, reduce its complexity, and represent it in a simplest form. One force vector with solving one axis of rotation only. Okay, and I think one of you actually asked this before. Some of you guys already asked this. Can we just simplify all the forces altogether and sum it up? That is actually true, and in fact, in most cases, it's a lot simpler. But the only reason why we go through the steps before is for you to understand the relationship on how force times perpendicular distance is applied to determine the moment of force or torque or simply moment. And what's the relation between a force vector and a position vector so that you're able to do cross product. So you're able to solve the moment of force mathematically. In this particular case, most of the sample problems is going to be given to you is trying to reduce the system or trying to replace the force or couple systems into its equivalent resultant force and couple moment acting at a particular point, in this case, particular point O. Okay, you will be revisiting concepts such as summation of forces, summation of force vectors in scalar and in vector notation form. So I hope you still recall them. If it's in magnitude, if it's in scalar form, so the force resultant is simply uh, the sum of all its x and y forces there. So the magnitude of the force vector resultant is simply the square root of the sums of the squares of its x and y components, essentially. And then if it's already expressed in Cartesian vector form, which will we be playing later, um, all you have to do is express each force vector. So force 1, force 2 in its Cartesian vector notation form, and simply do algebraic addition or subtraction, whichever is the appropriate sign for it. Okay, and then finally you will be getting uh, the angle in between the force vector and the moment vector. As for the moment, all you have to do na lang here is to simply get the sum of all the moments about a particular point, and sometimes we're given in a problem, we're already given a rotation or a moment, so to speak. So we have to include that as well. And also we'll be dealing also with other moments that are in couple or as equivalent couples. Okay. So here's it in vector form since it's naka-bold siya, and here's it's in italic, so naka-scalar siya. Okay? So again, this is the sort of concept that it's easier for it to be taught while we're doing or while we're solving a problem. So let's start with that. Okay, here we are with another sample problem. We're being asked to replace the force and couple systems shown in the figure below by an equivalent resultant force and couple moment acting at a particular point O. Okay, so we're given these two figures here and their equivalent. This is another way of showing their force vectors. This is their the x and y components. So we're here to get the equivalent resultant force and couple moment acting at point O. So this is point O. So in this case, there's no x and y axis, so we draw ourselves one here. So here's the x and y. Here's the force vectors, the x and y components, And then from here, we're given pretty much all the dimensions here. So all we have to do na lang here is solve them one by one. Okay? If you want, you can pause this video and try to solve this on your own muna. And then on your own, and then try playing it up if you're stuck, or if you can't still figure out the solution to the problem. Okay, let's try solving it. So several things in mind before we actually solve it, you know. So what is being required dito exactly? Okay, so we're being required the force, the resultant force. We're being required at what particular direction it's being applied to, and the moment about point O, the resultant moment about point O. Basically, the summation of all the moments being done in this particular figure. So for solution, recall that for getting the magnitude of the resultant force, you're required to have its x component and y component. So you have to square them and add them and get their square roots so that you will get the resultant force magnitude. And of course, the force resultant along the x-axis is equal to the summation of all forces, all horizontal forces here. And same with the resultant force along the y-axis. So you can get them by the summation of all vertical forces in the system. You can also get the angle by getting the tangent inverse of force resultant y over force resultant sub x. And then finally, all we have to do na lang is to get the resultant moment, or the total moment here, by getting the summation of all moment plus, forget to add here the, wait, let me just put something. And in this particular case, we're not given a given moment already. So sometimes a particular problem has already a given torque. So whichever is added there, okay? So since there's none in this particular sample problem, so it's just summation of all the moments involved in this particular forces. Okay, now let's try applying it. Okay, so we place our solution here. We know what to do. So all we have to do is just apply them and solve them one by one. So if you recall your lectures 2 and 3, it's lectures 1, 2, and 3. It's gonna be pretty easy to solve the force resultant because all we have to do is just get the summation of all the x and y forces to get our force resultant sub x and force resultant sub y. Okay, so let's do that first. So the first step here is force summation, and we get first the summation of all x. So what do we have here? We have 3 kilonewtons times cosine 30 degrees. We have 3 over 5 times 5 kilonewtons times 3 over 5. That's pretty much it. So all we have to do is just add them up. And then we get also for the y forces. So the force resultant for horizontal forces is 5.5981 kilonewtons positive. So if you notice here, we also indicate if it's positive, it's going to the right. It's just an indication of our reference point. Okay. So for y resultant forces, so we get the summation of all vertical forces, with up being the positive, down going negative. In this case, we have 3 sine 30 degrees minus 4 minus 5 times 4 over 5, because that is y component for this particular force vector here. And we get around negative 6.5 kilonewton, or 6.5 kilonewton downward. Now, since we have already the x and y component of our resultant force, the resultant force magnitude is equal to the square root and the sums of the squares of its x and y components, which is around 8.5784 kilonewtons. And then, of course, we can get its theta, which is about, you guess it's around negative, actually, negative 49.2634 degrees, or 49.2634 degrees clockwise from the negative x-axis here, going here. Okay. So the next here is getting the moment summation. So all we have to do is just get the moments of all the forces and in their equivalent perpendicular distances. So, yep, all we have to do is, the first one is we have 3 sine 30 degrees. Its perpendicular distance to moment O is 0.2. There we go. So that's the perpendicular distance, 0.2. And it's rotating counterclockwise, so it's positive. Next one is, let's try 3 cosine, 3 kilonewton cosine 30 degrees. So the perpendicular distance is 0.1, but since it's going clockwise, it's going to be negative 3 cosine 30 degrees times 0.1. Next is, let's try 4 kilonewtons. So 4 kilonewtons here, perpendicular distance is 0.2, but it's rotating clockwise, so it's going to be negative 4 times 0.2 kilonewton meter. And then finally, we have this 5 kilonewtons here. So 5 kilonewtons times 3 over 5, that's going to be counterclockwise. So that's perpendicular distance is 0.1. That's positive. And then 5 times 4 over 5, that's going to be negative since it's clockwise. And the perpendicular distance is 0.3 plus 0.2, which is 0.5. There we go. And we evaluate this further. We have our resultant moment equals to negative 2.46 kilonewton meter, or 2.46 kilonewton meter with the counterclockwise, with the clockwise symbol. Okay. And finally, to visualize where it is, we draw it by a diagram. So here's the figure. This is not FBD, this is a diagram. And just to imagine just where it is, the X and Y components. So we put the FRX and FRY here. Let's not forget the X and Y components where they are. So this is the X, this is Y. There we go. And then that's the resultant. This is a resultant force sub X and resultant force sub Y. This is our resultant force, and then it's theta. And then the moment, the resultant moment is here, which is which is clockwise, so it's negative. Okay. So if I ask you to visualize where the force resultant is, I want it to look this way. You don't have to do the entire diagram. I just want to see. I just want to make sure you guys can visualize where is it coming from. But I just need to see the X component, the Y component, and the resultant force plus the angle, and of course in which direction the resultant moment is. So, and then just add the values here, plug and play. Okay, let's try. Okay, let me just see. Okay, there we go. Let's try one more problem. I got 2 more. Okay, for another one, yeah, I think this is a pipe installed sideways, and it's a particular inlets. So we're being asked to replace the force and couple system acting on the member in figure drawn below by an equivalent resultant force and couple moment acting at point 0. Okay, so several things here. We have the core difference between the first problem and the second one is, okay, we have a few things in common. First, we have 750 newtons here pointing downward. We have 500 newtons here, and then we have what we call here a couple moment. It's a couple moment, if you recall, because it has the same magnitude, 200 newtons, and opposing direction then they are both parallel to each other, and they're separated by a perpendicular distance. In this case, measured at 1 meter. Okay. If you want to solve the problem on your own first, you can pause this video and give it a go. Okay, let's try solving it. So again, what is being required here? What's happening? All right. There's an animation. There's an animation lag, so that's fine. All right. So what is being required here? Again, we're here to look for the resultant force, its angle. That's a must, and of course the total resultant moment here. So first thing we gotta do is, of course, force summation. How do we do that? We get the summation of all the x forces and the summation of all y forces accordingly. Let's start with the x. So we have here 500 newtons, and then we have its slope triangle relation here. So the horizontal force here is 3 over 5 times 500. So we got that. And it's going to the right, so it's positive. What else? We have 200 newtons going to the right and 200 newtons going to the left. So that's going to be canceling out. And that's pretty much it. So we have here 300 newtons. For the y component, we have 750 newtons and 500 newtons pointing upward. So that's 500 newtons times 4 over 5 upward. So that's positive minus 750, which will give you negative 350 newtons or 350 newtons pointing downward. Okay, this is just for another way of representing it. Okay, if you recall your statics. Yeah. Okay. So now that you have your x and y components for your resultant force, all you have to do is just square them and get their sums, and then get their square root as well. So you will get your you will be able to find out determine your resultant force, which is equal to 460.97 newtons. Okay, and you can get the angle, which is the tangent inverse of the y and x component, and you will get negative 350 over 300, which is negative 49.40 degrees or 49.40 degrees clockwise from the x-axis. That's a better way of actually describing it, so that it's a nicer way of putting it there. Okay, and then since you already done this, all you have to do is just get the resultant moment. Since we have this, we have each of these force produce a particular moment, so is this couple moment here, so we have to add that as well. Okay, the couple moment is a free vector and can act at any point. So meaning it can slide here, it could be here. So we just add it there. Okay, and we can use the equivalent couple method to determine the moment of force here. So that's basically 200 newtons times 1 meter. So that's gonna be negative 200 Newton meters is going. It's actually positive, you know. It's going counterclockwise. So it's positive 200 Newton meters. So we'll just figure that later. Let's do this first, since it's the one thing that we already know. So for 500, we have 4 over 5 times 500. It's gonna, and the perpendicular distance is 1.25 plus 1.25, so that's gonna be 2.5. But it's gonna be counterclockwise, so it's positive. There we go. And then let's try naman yung horizontal force, which is 500 times 3 over 5, which is gonna be, again, clockwise direction. So it's gonna be here, yeah. So that's gonna be negative times 1 meter. And then let's try naman yung 750, which is gonna be clockwise. So 750 times 1.25. And then, of course, finally, positive 200 times 1 meter. So that's going to be Newton meter. And then you simplify this, you will yield negative 37.5 Newton meter or 37.5 Newton meter with the clockwise symbol, negative clockwise symbol. Okay. Okay. So to visualize it, these are your forces are. So it's gonna be here. Again, you draw your x and y components, and then you draw. These are this is your x and y your x and y diagram coordinates first, and then this is your resultant force of x, your resultant force of y, and the resultant force mismo, and then this is the theta. And then of course the moment resultant rotation, which is 37.5 Newton meter. Don't forget the negative symbol here. There we go. I think I wasn't able to animate it anyway. Okay, just don't forget that. Okay. So we've solved two dimensions here. So it's time for one 3D sample problem. Okay. So here we are. Okay. So several things. Okay, there's a lot going on here. This is a particular beam, and we're here to the structural member, and it's subjected to a couple moment M and a forces F1 and F2 in the figure shown below. The problem wants us to replace this system by an equivalent resultant force and couple moment acting at its base point O. Okay, so we have the X, Y, and the Z axis here. We have, well, what do we have? We have two position vectors automatically. We have forces acting on the top of the beam here, at least on its cross section. So we have force 2 here and force 1 pointing downward, and we have a moment given already at 500 Newton meter. Okay, how do we solve this? Since this is in 3D and there's a lot of forces going on here, remember, if there's a lot of forces going on, it's best to express everything in Cartesian vector notation. And of course, the rules when it comes to solving, the rules when it comes to replacing an equivalent resultant force and a couple moment, and in 3D, you have to express the answer in Cartesian vector notation. Always, at least for simplification of force and couple systems. Okay? So the first thing to do is, of course, you know what to find, which is resultant force in Cartesian vector notation, as well as in resultant force in Cartesian vector notation. So just like I said, steps should be the same, except the force resultant and the moment resultant are in Cartesian vector notation in its final answer. So what can we identify here? We know for a fact for F1, it's particularly easy. F1 is only containing k hat. So it's F1 is 0 I hat plus 0 j hat. Since it's pointing downward, that's negative 800 k hat. Okay? For F2, it's a little bit tricky, but if you still recall, since point C to B here is it's a unit vector, we can get the unit vector here by getting the quotient of the position vector CB over its magnitude, which is represented in this equation. So this one. So we have dimensions here, that's 0.15, 0.1, and 1 meter. So all we have to do is determine what is CB. And recall that RCB is basically RB minus RC. Okay, and this is negative 0.15 minus 0, I hat plus 0.1 minus 0, j hat 1 minus 1, k hat. So it's basically the coordinates of B, subtracting it to the coordinates of point C. So for point B, we have negative 0.15, positive 0.1, and 1 meter k hat. And then for point C, it doesn't have a x component, so that's 0 I hat. It doesn't have a y component, so that's 0 I hat. But it does have a z component, so that's 1 k hat. There we go. And you will have this one. So negative 0.15 plus negative 0.15 I hat plus 0.1 j hat divided by the square root of the sums of negative 0.15 squares plus 0.1 square. And you will have negative 249.615 I hat plus 166.41 j hat. Okay, so far so good. We have now we have F1, we have F2, and then of course we need to identify how can we convert this into its Cartesian vector form. Which is a lot actually easier, since we're given a slope triangle here. We're gonna take it as any particular vector. Okay. So the 500, it's the x components negative 500 times 4 over 5. Doesn't have an x component pala, since it's running along the y axis. It's gonna be negative because it's already in the negative y axis. So that's negative 500 times 4 over 5 j hat, and then the z component pointing upward. So that's 500 times 3 over 5 k hat, which is equivalent to negative 400 j hat plus 300 k hat. But we're not yet done. Since we already got the force vectors for F1 and F2 in its Cartesian vector notation, we just simply add them to get the resultant force vector. If you recall this one, yeah, so you just get the sums of this, and you will yield negative 249.615 I hat plus 166.41 J hat, negative 800 K hat newtons. Don't forget the brackets and the unit. Okay, let's just move that aside lang muna. So there we go. Now, since we already know that, all we have to do na lang is, no need to find for the angles because these are the coordinates itself. Next here is to identify naman yung resultant moment here. And recall, the vector is the result is a summation of moment m about point O plus other moments here, this one. So in this particular case, this is a vector moment. So a vector, meaning we will be doing cross product. How much for cross product? In fact, we'll be doing two cross products because we need to get the cross product from RC cross F1 and RB cross F2. But you will soon realize that it's gonna be a lot simpler. And then of course you just add the given moment here, 500 Newton meter in Cartesian vector notation, which is negative 400 J plus 300 K. Okay, I'm not putting the units yet, but these are all in Newton meter naman. Okay, so for RC cross product cross F1, it's basically here. That's their indeterminate form. You can see there's a lot of zeros going on here. So obviously this will automatically cancel out. Kasi zero. Kasi if you're gonna evaluate it, it's gonna be 0 times negative 100, 1 times 0, so 0 kaagad yun. And then for the J component, 0 times negative 100 and 1 times 0, 0 kaagad yun. And if you're looking for the K component, so that's 0 times 0, 0 times 0. So essentially, this particular determinant is equal to 0. So all you have to evaluate na lang is yung position vector RB cross force vector F2 in this case. So, and then from there, you reduce it to solving it algebraically by addition and subtraction. So you simplify further. So let's just organize it. Here are the zeros. So cancel out. This apparently will yield the 0 when you multiply and subtract them together. All you have is all you're left with is negative 166.41 I hat, negative 249.615 J hat, and then plus negative 400J and then plus 300K. Simplify further, you will yield the answer of the resultant moment in Cartesian vector notation as negative 166.41 I hat minus 649.62 J hat, and then plus 300 K hat Newton meter. All right, before anything else, how to visualize it. Essentially, all you have to do lang is just to determine where it is gonna be. Okay, so we have the force resultant here, and the particular coordinates, the x, y components are. So we have roughly an idea where it is. At least for force resultant, it's gonna be somewhere here since we have a negative x component, then I hat, so somewhere here. We have a positive y component, j hat, so it's somewhere here, and then a negative one, so the end point should be something pointing towards here. Now for the resultant moment, the axis of rotation is somewhat in the negative x-axis, negative x-axis, negative y-axis, and positive 300. So it's something like this one. There we go. All right. So again, I hope you had fun solving this particular problem and the rest of the sample problems. If you're having trouble understanding, that's okay. That's fine. All you have to do is just go back and try to solve it on your own. And then once you finally understand the process and what's being required, you can try solving more sample problem in the book. And with that, that concludes the force system resultants. Actually, I left a few things, but I'll just discuss it in the following lesson. I'll put it there. And I want you to enjoy the holidays and rest out first. But don't forget to warm up. But don't totally rest. I just want you guys to keep your solving hand warmed up. Okay, so I'll be sending a few problem sets over, and hope you guys solve them accordingly, and that we can discuss online on our next meeting.